Sorry? Live, okay, good.
So hello everybody. So thanks for coming to the seminar of Artur Palha, who is visiting us for 2 weeks. Well, he has been here almost for 2 weeks now. He's leaving on Friday. And I meet him in the Commas Congress this summer, and I found his talk very interesting, and I was working on related things. So we are trying to collaborate, and he's going to give, well, he did the PhD in Delft University, and then he made a postdoc, another year postdoc in Delft University, and then he moved to Eindhoven to do a second postdoc, and then he got a permanent position in Delft University. And today he's going to talk us about the structure preserving discretizations from structure to results.
Thank you, Daniel, and thank you for inviting me and for the Institute for hosting me. So, as Daniel said, I'm going to be talking about structure preserving discretizations, and so the idea is to go how to identify the structure and the results. But so the way I'm going to try to do it is that I will try to give some motivation of why it's important to look at the structure. And the motivation is that if we just do standard approaches to numerical discretizations, or let's say the standard ideas of minimizing truncation error, typically, or most of the time, things go wrong. And then it's because things go wrong is that why we need to think about different ways of discretizing. And structure preservation is, in my opinion, is one, let's say, structured way or formal way of doing this. It doesn't mean that there are not other ways of doing good numerical discretizations. And for doing that, I will try to use Maxwell's equations because they are like a good place to do this, because if you don't satisfy the structure, then things really go wrong. Fluids, they also go wrong, but you can get away with some issues in a numerical discretizations. And if I have time, I will try to go to time-dependent problems, but only if I have time. So, for the motivation. Before that, so if you have any questions, feel free to interrupt and just ask me. So motivation. So a very known issue that we have in Navier-Stokes is the so-called checkerboard problem. I think most of people here know it, and it can very easily be seen for Stokes flow, which is one of the simplest ways of thinking for Navier-Stokes. And this appears if we use a kind of a collocated grid. And by collocated grid, I mean I place all my unknowns in the same positions in my grid. So I have a grid and I place everything there. So my pressure and my velocities are placed there. This is just a simple 1D case to show this. And the problem appears first because of the collocation, and the second one is because we use, together with this collocation, we use these central differences for the definition of the gradient and the divergence. But let's say this is the standard way of computing the divergence, the gradient with the central differences. And we can see that, okay, if we do the limit where delta x goes to 0, well, this is just the gradient, or let's say the derivative in the x direction. This is just 1D. And everything should be fine, right? But in fact, it's not fine because we are never in the limit of delta x going to 0. We are always in the limit where delta x is actually a finite value. And this gives some problems. And we can see it in this way. So if we use this discretization for the differential operators, and we discretize our Stokes flow, this is the form of the algebraic system that we get. And typically we get this B here, which represents the discrete gradient. And then we have still the transpose of B, which gives us our discrete divergence. And this is, so far it's fine because we also have the same properties at the continuous level. Now, if we try to solve this problem, we can use a Schur complement, and this is the solution that we get, or let's say the expression that we get in order to get our pressure, right? Now, everything is fine unless B has a non-trivial kernel or a null space. If that is the case, then I can plug in here any element of the nonlinear kernel of B, and then this solution will not be well posed, right? So I can always add one element of the null space, and it will still be a solution of this. So this is mainly the problem of checkerboarding. And you can see that, in fact, this B that comes from discretizing the gradient has a non-trivial kernel, and that one is this solution. So any solution of the type A, B, A, B, A, B, so forth, is a non-trivial kernel, right? If I put it here, A minus A is 0. If I divide by a non-zero value is 0. So at the discrete level, this function has a 0 gradient, which is clearly not true, and that's an issue. So many of or most of the solutions to address this problem, they somehow boil to some kind of stabilization, which somehow boils down to adding some non-zero term to this part, such that then this equation becomes this, and we can actually solve it. But we solve the problem of the checkerboard, but we add problems because now we don't have this equation that should represent the incompressibility, but we have now this equation that has a source term, right? Although beta is typically small, this will not be 0, and we are essentially violating the incompressibility of our flow. So somehow there is a kind of a trade-off into having a proper solution for our pressure and introducing either some problems on incompressibility or on energy conservation or something like this. It's also known in the literature that, let's say, the best way to solve this checkerboard problem, in the sense that this does not appear, is instead of using a collocated grid, to use a staggered grid. So we place our pressures at center points of the cells, and then we displace our velocities and we place them in the faces of the cells. Now, if we do this, then this works well, and we don't have any checkerboard problem. Now, what I will try to discuss here is that this is a specific case following structure-preserving discretization. So this is one concrete example of a structure-preserving discretization. And the idea is to, okay, how can we formally, in a general sense, reach this type of discretizations without being an ad hoc? So if there is a kind of a way to systematically find this type of discretizations, that's the idea of this. So another example is this one. Now for finite elements, is this for elasticity. So there was this problem with a Sleipner offshore platform where they were trying to kind of design this platform to be at the sea, and they wanted to design the structures that could support the whole platform. And they did finite element analysis, and one of the equations that has to be solved is equilibrium of forces. So if the platform is in equilibrium of forces, everything is fine and everything works correctly. So it doesn't break, etc. Now the problem is that if you use standard finite elements, which is equivalent to collocated points for finite differences, so just standard Lagrange interpolatory basis, this equation is not solved strongly, in a sense that if I plug my interpolation of my discrete solution for sigma, this is not exactly 0. It's only 0 in a weak sense. So in finite elements, just in an integral way, this is 0. So just the integral of this is equal to 0. Now, the problem of that is the following. So this is just a simple case for the Poisson equation. It's not this one, but just to illustrate this. Now, if I use nodal basis to represent phi, I have the same problem. So I can exactly represent this gradient, but then the divergence, I do integration by parts, and then the divergence is weakly satisfied. Now, if I solve this equation, I get my phi. This is the error that I get for phi. But if I take my phi, and I compute the gradient and then the divergence, and then I interpolate that, this is the error that I get. So you cannot see it here, but this is 0.6. So it's several orders of magnitude larger than this. The point is that because this is not exact, whenever you do this divergence, you are adding errors to this. So the problem here is that they looked at the solution, and the solution was telling them, okay, the error is relatively small, but in fact, the actual error on this equation was quite large. So there was not an equilibrium in the design system, so it kind of broke. That was a problem. It was a catastrophic error that then people had to rethink how to do these simulations. So another case is electromagnetics. And so this is a curl-curl eigenvalue problem. And this is typically what you get if you are trying to find some kind of the eigenmodes of an electromagnetic cavity, so a resonating cavity. So these ones, we know we can, on a box, if the domain is just a simple box, we know the analytical solutions are given by these signs and sign functions with different integers m and n. And essentially it tells us that the eigenvalues are just the sequence of integers. So, and these are the expected eigenvalues. Now, if we just use standard Lagrange basis functions in finite elements and this type of grids, and we try to find the eigenvalues, the discrete eigenvalues, this is what we get. And if you refine the mesh, we just get more points, and maybe the curve shifts, but it's still a kind of a continuous curve. It just doesn't resemble at all the eigenvalues that we should get. What is surprising is that if I just change this grid and I go from this to this so-called crisscross grid, then I can converge to the eigenvalues, but not to all of them. Some are spurious, so they are unphysical eigenvalues. So this could be okay, because if I don't know anything about my system, I would say, okay, I expect some kind of discrete eigenvalues, and I see these and okay, there is something wrong. But if I would get something like this, then I do not know if this one is spurious or if this one is spurious, because I don't know the actual solution. Now, in electromagnetics, people know, in the same way as they were using staggered grids for computational fluid dynamics, that if you use another type of basis functions, so these are called Nedelec basis functions, these are vector basis functions, so something similar to the staggering in computational fluid dynamics, then no matter what is the mesh, we always can approximate the eigenvalues. We don't get any spurious eigenvalues, right? So this means that indeed we can find correct discretizations, but there are some discretizations that do not work properly. So the question here is that how can we construct stable and consistent discretizations, in a sense that, so if we have stable and consistent, by the fundamental theorem of numerical analysis, we can know that they are convergent, right? That's the whole point of doing this. Now, my claim, or at least what I want to discuss in this talk, is that if we look at the underlying structure of the PDEs and of the differential operators, and I identify this structure and I try to represent these structures at a discrete level, then I'm kind of guaranteed to get stable and consistent discretization. So I don't have these problems that I was discussing before. So I will just try to discuss, not in concrete terms how we can exactly do it, but the general properties that we need to satisfy in order to have this discretization. So and I will use Maxwell's equations as an example, because, as I said, in Maxwell, in electromagnetics, if you don't satisfy the structure of the PDEs, we just don't get any results. So it's nice because you cannot do anything wrong, or you should not do anything wrong. So electromagnetics, so this is Faraday's law, Ampere's law, and these are just some Gauss's equations. So this one just relates loop integrals of the electric field with variations of the fluxes of the magnetic field which are orthogonal to these loops. The same for this magnetic field and this electric field. And there are these two equations that tell us what are the sources for the electric field and for the magnetic field. For the electric field, we have the current, the charges. For the magnetic field, there are no magnetic monopoles. Now, how do we go about these to do discretization? Typically, what we do is that, okay, we just find some discrete representation of our fields, which typically we just make a mesh and we just sample the field at some points, right? This is what I mean. This is just vectors with samples of the fields at points, all of them at the same location, for example. And then we just, based on this, we just write some discrete versions of our differential operators. So this is G, the discrete version of gradient, C, the discrete version of curl, and so forth for the divergence. And then one thing that we don't do, but we know, or let's say we expect, is that if I take an analytic field E, electric field E, and I just discretize it, so I just interpolate, so I just sample it at my points in the mesh, I compute my discrete gradient of it, and I make the difference with respect to the analytical curl of this, sorry, curl. The idea is that if I refine my mesh, this goes to 0. And I can do the same to all the other unknowns using all the other operators, and this should all converge. This is the underlying idea that we always have, right? And we think, okay, this works, so we are good to go, and we can just take our equations, take our discretizations, and just plug it in and get a discrete version of our equations. This is what we typically do, and this will likely fail, or most of the cases, if we just use, for example, central differences with everything located in the same place, or just Lagrange interpolants, this will fail. And the question is, why does this fail? So there is a long discussion of this, and then there is a kind of a shorter one, and the shorter one is what I will try to do. So the idea is that these are the equations, Maxwell's equations, and these equations are self-consistent in a sense that this one is connected to this one, and this one is connected to this one. And if we fail to satisfy this consistency, then essentially one equation is pushing the solution in one direction, and the other one is pushing in the other one, and that's why we get a kind of an unstable solution. Now, to see that, we know that, okay, we have the divergence of B is equal to 0, so we can compute the divergence of these equations. So we take the divergence here and divergence there. And mathematically, this is not numerics, is not modeling, is mathematically we have this identity. So the divergence of any curl of any vector field is always 0. So this term will automatically be 0. And what we get is that the time derivative of the divergence of B is equal to 0, which means that if we start with a divergence-free magnetic field, this equation will never break this condition, right? Will remain divergence-free. Now, if I do this at the discrete level, if I try to compute the discrete divergence of the curl, this is not necessarily 0. And in most numerical discretizations, this is not 0. So it means that at the discrete level, we are adding numerically some sources for the magnetic field, which is incompatible with this equation. So our solution will be physically inconsistent. That's the point. So the same for this equation. The idea is the same, but now there is these two equations imply conservation of charges. And if we do it discretely, essentially what happens is that we are generating some charges in the domain, right? Yeah, so if we put all this together, as I said, some equations are pushing in one direction and other ones are pushing in another direction, and this does not work. So although this converges, if we actually solve it and we plug it in here, this does not converge. So the solution to this equation does not converge to the actual solution of this. Right? So the underlying idea of this is that, is this structure, yeah? Because the problem is that the behavior of the equations is not continuous. So only in the limit of infinitely small mesh size, the discrete equations will behave like the continuous ones. That's a problem. Yeah, but the point is that some things you can do approximately. So for example, I will discuss which equations you can do approximately, but I have it here. These ones you cannot do approximately, because this breaks for example, the topology of the equations, and this gives you a completely different solution. So I will also make a list of other things. So even for Helmholtz decomposition, where you can decompose your vector field, for example, in a curl-free part and a divergence-free part. If you break this type of properties, you automatically break these, and then you are mixing divergence-free parts with curl-free parts, and that pollutes completely your solution. That's the problem. And this transition, so that's the point. So this in fact converges. So if we look at the approximate values, this converges. But the structure of the PDEs and the allowed solutions do not, well, they do this, but only in the limit of h going to 0, of h0, not going. So there is a discontinuity when we do that. I mean, you saw it in the checkerboard problem. No matter what the size of h, it will always have this case, right? Only in the limit it's 0, then it will not be the case. Any other questions? No. So the point is that there is these identities are the same, so the divergence of the curl is always equal to 0, and then there is the other one, which is the curl of the gradient is always equal to 0. Was not used in this specific case, but is the other one. So this is a bit of a confusing slide and a bit too much information, but I will try to explain it as best as I can. So the underlying idea is that I can have some spaces which are essentially some boxes or containers where I can put my different unknowns in a PDE. And in 3 dimensions, I only have these 4 boxes. That's what I'm going to claim, and I will try to justify why is that the case. So in my case, for Maxwell's, I have phi, which are the scalar fields. I have the electric field E, magnetic H, D, B, and J. Now, looking at these equations, I can try to start putting them in some look. I already put them there, but we can see what are the properties of these. So the idea is that if I have E and H, in this equation, I will need to compute the curl, right? So to everything that is inside this space, which I call H curl, I will need to be able to compute curls. So however I define them, it has to be defined in a proper way that I can properly define the curl operation in that. So in functional analysis is the H curl space. Now, the point of this is that if I apply the curl to every element of this space, I need to be able to be mapped into the H div space, right? And the reason for that is that if I do the curl, this is equal to B, and B is something for which I can compute the divergence. So this is a structure. But I don't map it to any specific region of H div. I map it into the null space of the divergence, right? Because I want that the divergence of the curl is equal to 0. So this is an important structure. I can do the same for this case, but with the gradient. So anything that I need to compute gradients, I can do the same. And I can do something similar for the divergence. But there is nothing else, so there is no kernel of this space. So this just identifies to us that if I have, at a continuous level, I have these different structures, right? These spaces where I have things. And in fact, this is a known structure, and it's called the Rham complex, and this is an exact sequence. And it's an exact sequence because, so it's a sequence of spaces, and it's exact because there is an operator that maps from one space to the other one, and if I apply twice the operator, this is 0, right? The curl of the gradient and the divergence of the curl is equal to 0. So this is one structure that I will focus on that is important to essentially encodes the consistency of these equations, right? But this is not enough because I have these equations, but I also have these constitutive relations that relate D to E and B to H. Which means that I can replace D here by E. So E epsilon is just this theta1 to be more general. So I can do that, and then I would need to compute some kind of divergence on this theta times E. The point is that, so I need to be able to map it from this space to that space. The point is that I want to highlight, this is not very obvious at a in vector calculus, but in differential geometry it is that this divergence is not the same divergence as we have here. It's unfortunate that the same notation is used, so I will call it delta divergence. So I have the normal divergence that we use, which maps from this space to here, and when I am in this space, H curl, and I need to compute a divergence, and I call it this tilde on top. I just call it tilde because if we are in the context of functional analysis or finite elements, this one appears as integration by parts. So it's not a strong divergence, it's a weak divergence. That's the reason why the tilde. So I can do the same for the curl, and I can do the same for the gradient. So this one is not the same as that one, this one not the same as this one, and these two are not exactly the same. So this means that we have, in fact, two exact sequences. So I can write one sequence on the top, and there is one on the bottom, and there is some connection with these operators or coefficients. So what I want to tell you is that the idea is that if you discretize your equations in a proper way, you can exactly do these operators. So what we think is the most difficult part, which is the differential operators, in fact, they are almost trivial, or they can be done exactly, of course, exactly on your degrees of freedom. The problem of every numerical discretization where the numerical approximation appears is in this connection between these two spaces, and we always have to do that. So for example, if we want to compute the Laplacian, for example, we have something in this space, we can compute the gradient exactly, then we have to connect to something in this other sequence in order to compute the divergence, and then we have to go back. So it's in these steps where we have this numerical approximation. Okay, this is just a highlight. So this seems a bit artificial in vector calculus. If we use differential geometry, which I will not discuss, this is just a highlight, this is explicitly highlighted. So there is a clear difference between these two things, and there is this codifferential operator, which is this tilde divergences. Now, I will also not go into details, but the point is that this structure that exists just because we define our differential operators as they are, it means that we have all these mathematical properties here, which is what was the question before. So if we construct some approximate discretization that breaks this structure, we destroy all these, and then our numerical discretizations are just badly defined. So my point is that if we want to represent these at a discrete level, we somehow need to construct this. So we need to find some discrete spaces for H1, H curl, H div, and L2. So these spaces S, D, C, and G. And we need to construct associated discrete gradients, curls, and divergences, such that this constitutes a discrete sequence, as we had for this continuous one. And we need to have something that connects the two things. So in the discrete world, we have the same mathematical structure as in the continuous world. Now, the point is that you can say, okay, I can give you any set of discrete spaces, and this does not tell you that the actual approximation is good. So what tells us that the approximation is good is that we need to provide some way of discretizing our field, so going from the continuous space to the discrete space, so either sampling it or something like this, and we need to be able to interpolate it. So we need to have some kind of basis functions that, given the degrees of freedom here, we can reconstruct and get kind of not a smooth, but at least piecewise continuous solution or smooth. And by doing this, we kind of link the discrete world to the continuous world. So how can we construct this type of structures? See how much time I have. So there are many ways of doing this. This is one way that I particularly like because it gives some insight on how to do this, and it's relatively easy. So the idea of that, and I will use the board because I think it's easier. So let's look like this. If we want to represent this equation, gradient of phi equals to some vector field V at a continuous level. Let's say I have this very basic mesh where I have these points, V1, V2, 3, 4, V6, and I have these edges, and so forth, right? I can rewrite this equation in an integral sense, right? I can do the integral over an edge of gradient of phi, and this is equal to the integral of this dot tangent, and I can do the same for the field V dot tangent, and I integrate over E. I can now use the fundamental theorem of calculus to rewrite these as phi, so let's play ij, as phi of Vj minus phi of Ei. This is just equal to the integral. Yeah. So the point is this. So this kind of, I can use this way to kind of say, okay, this can be my discretization for phis. So just sampling it at points. I can put P1, Phi2, so forth. And this can be my discretization for fields for which I want to compute my curl. So I can say that my Vij is just equal to the integral of V dot the tangent E. So this is what so I can also do this for the curl using Stokes theorem, and I can do the same for the divergence using Gauss theorem. So for Stokes theorem, I would relate, in this case, in 2D circulations with surface integrals. And if I was in 3D, I could use Gauss theorem to relate fluxes to volume integrals. That's the point. So I can discretize my unknowns, so I can find discrete spaces or discrete ways of representing my different unknowns in these spaces in using this way. Yeah? For example, for this space is just evaluations at points. For this space is just line integrals. For this space, fluxes over surfaces. And for this space is just volume integrals. And then the standard gradient, curl, and divergence are just given by the fundamental theorem of calculus like this. So the next point minus the previous, or circulation. So in this case would be plus, 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 minus. Yeah. So now this is okay to actually do this part. So I know how to discretize. It's this geometrization I said. I also know how to compute these differential operators. Now what is missing is how to interpolate it. So I need some kind of functions that allow us to go from these discrete degrees of freedom, let's say values at points, integrals over lines, and so forth, to some kind of field. Now one way to do that is by using nodal bases and this so-called edge bases. So nodal bases are like Lagrange interpolants. So they are 1 at a point and 0 on all the other points. So it means that if I have the values of a function at these nodes of the grid, and I multiply every value by each of these basis functions, I get an interpolatory function of this. Now these edge basis functions are exactly the same, but now for the integrals. So if I have something or a coefficient that tells me the integral of a function in this interval here, and another coefficient for the integral in this interval, and so forth, and I multiply by each of these basis functions, I have a polynomial whose integrals over these intervals is equal to the original function. It interpolates the integral. So I can do tensor products of these, and I can just reconstruct any of these spaces. So the point is not the details, it's just to know that the idea is that there is a geometric way of getting these discrete degrees of freedom, and then there is a way of writing some interpolation functions that allow us to do. Now, the good thing of this is that this generalizes to curved meshes, because you can see that what I wrote here, for example, for this edge, it's valid on this rectangular grid, but if I completely deform this grid, it's also valid. It's exactly the same equation. It just matters the topology of the grid. I will just skip this. No, there is one point here that is important, right? The reason for this is that we can do this on one grid, but if we want to do this second sequence, we need to have a staggered grid. And then we need to connect the two, and this is an issue. But I don't want to discuss. But the point, this can be solved. The point is that the way in which you define this connection dictates what kind of numerical method we are doing. So for finite elements, there is one way of connecting these. For finite difference, there is another way, and so forth. So this is what I was trying to mention. So for example, for this connection, there are these approaches, for example, de Bruyn, Irani, and Tonti. And what they do to connect is that they use two grids, and finite elements, you kind of do integration by parts to construct this. I will skip these now because these are a bit too many details. But the idea is that we can use these to solve this kind of time-independent problems, so stationary problems like Poisson-like, potential flow, Darcy flow, and so forth, and this works well on highly curved grids and so forth. Now, any questions on this, or okay, we'll go to the time-dependent problems. So when we add time, so there are two approaches for kind of doing this. So one thing is that we could use the same approach that we were discussing before, going to differential geometry and working on four-dimensional spaces. That's not what I'm going to discuss here. I'm going to discuss the issue with the time-dependent problems and how we need to rewrite the equations in a specific formulation for the discretization to work. Now, this is one case. So we know that we have a pendulum, and this is the exact solution. And we have different numerical discretizations. So these two are non-structure preserving. This one is low order, this is high order. But it doesn't matter. They both behave in an unphysical way, right? One adds energy, the other one removes energy. And the structure preserving one just preserves, okay, it has an error in the phase, but preserves the oscillatory behavior. So it doesn't add or lose energy to the system. So another thing that we also see in time-dependent problems, for example, in the passive advection of something, is that there is time reversibility, right? If we passively advect something forward in time, if we reverse the field or we reverse time, we should go back to the original solution. And this is, for example, one case on a very unresolved grid in which we can actually go forward and we go back and we get the same solution. So this is something kind of behavior that should be expected also from the numerical discretization if this has at a continuous level. Now, depending on the PDEs that we are trying to solve, there are certain invariants that appear on the PDEs. For example, energy, if we are solving, in this case, fluids, enstrophy in 2D, helicity, if we are talking about 3D. If we are in MHD, there is cross-helicity and magnetic helicity. So these quantities are conserved. Or, for example, entropy is kind of grows in a specific way or changes in a specific way. Now, these are constraints to the dynamics of a problem that if we don't satisfy this at the discrete level, we are somehow allowing the solution to drift into regions which are not the physical solutions. So the question is, how can we try to do this? So one example is the Burger's equation in 1D. So we can write the Burger's equation in a conservative form or in an advective form, right? The two equations are equivalent at the continuous level, right? I can go from this one to this one exactly, right? But this does not hold at the discrete level. So if I take this form of the equations and I use central differences, this is what I get for the nonlinear term. And if I use central differences for this term, this is what I get for the nonlinear term. And the two are different from each other. And they will have different properties. So even if I followed all the things that I was telling you about in the first part of the talk, and I did everything correctly for my discretization of the differential operators, if I start from different points which are equivalent at the continuous level, I will get a different discretization. And what is disturbing is that each of them will have different properties. So these ones are not going to be conservative, but if I combine the two and I get this formulation, so I just get 2/3 of these plus 1/3 of these, and I discretize these, I get this discrete form that is q-symmetric and telescopic, so it conserves both energy and momentum. So it's the same discretization, I just started from a different point. Yeah. Exactly. Exactly. Yeah. 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 Yeah, and in fact, yeah. For example, there is one way of doing this is that, for example, you can either follow Lagrangian or Hamiltonian formulation, and then you do that and you get the correct form of the equations, or you can even do already a discrete Lagrangian formulation, and then you get, no matter what kind of discretization you put there, you can get the correct thing. But this is just, it's exactly what you're saying. So the point is that many times you see that people are tempted to just go from one to the other one because it's just, I can do it analytically, so they are the same. But in fact, they are not the same at the discrete level. And this is just to highlight that. So with this in mind, yeah, this is the shallow waters equations. So I just go quickly over these just to show. So yeah, it's a bit difficult because I cannot show on the other side. So this equation has these conservation properties. And we kind of, after a lot of trial and error, we kind of came up with this form of the equations. So yeah, we introduced this Q, which is here, which is a kind of related to the vorticity, but is not exactly the vorticity, is represented in this way. And we added some additional variables. And then by doing this and applying the discretization, we can conserve all these things at the discrete level. So I will skip this because this is just using what I discussed before. This is just the discrete version that we get. But the point is that to reach this, that was one of the first attempts that we did for time-dependent problems. There was a lot of ad hoc work to try to find, okay, this works, this does not work, how can we change it, etc., etc. Yeah, and this was nice because it was worked on a sphere, and yeah. This is just some solutions. It goes up to day 7, and just to compare to some reference results in the literature. This is what we got, and this is what the literature has. So we used something like 6,000 degrees of freedom, and the literature used something like 500,000 or something like this. And the point is that you see some oscillations, but as you go forward in time, so as you do a longer time simulation, you see these yeah, high frequency oscillations increasing, and the simulation breaks after the simulation, say, day 6, and we can go forward in this. So again, that's the same discussion. Now, going to what was mentioned before, so what we did was a very ad hoc way. So the second approach that we did was actually to try to, okay, can we write the Hamiltonian for this? And this was for the Euler equations. So when we wrote the Hamiltonian, which was just the kinetic energy, the potential energy, and the internal energy, which are written in this way. And then we went for the derivations of these, the variational calculus for these. And what we got is that, okay, the energy conservation is just a time derivative of the Hamiltonian. And it's just written in this way. So if there are these unknowns A, this is the expression that we have. And the Hamiltonian dynamics tells us that dA dt is equal to this BH, where B is just this very large matrix. This is what Hamiltonian dynamics gives us. And this is 0 because this matrix B is q-symmetric. So if I have something inner product with the matrix B that is skew-symmetric with B, this will always be 0 because B is skew-symmetric. Now, because we follow this approach, we got the correct formulation for the PDEs. And if we just applied the numerical discretization techniques that we discussed before, this is what we get at the discrete level. And this one is also skew-symmetric. And because of that, we'll automatically conserve the energy and some other invariants of the system. So this is what was being mentioned, is that we can either do it very ad hoc way, trying to fit how can we write the correct formulation, or we can try to do a more systematic way. And I think Hamiltonian or Lagrangian dynamics is a good way of doing that. It gives us the correct formulation for which we can apply directly the discretization. And then we get a discrete system that has the properties of the original. So, and this is just to show that, okay, it has all the correct transfers of energy between kinetic, potential, and internal. So I had more things, but I think I will just skip them. And I just want to briefly discuss this one. So this is another approach that we are also working on, which is the following. Instead of having only one PDE, so this is Navier-Stokes. So using this formalism of having this box or these function spaces for my unknowns, I can represent the velocity, the vorticity, and pressure in these spaces, or I can also write it in these other spaces. These are, I'm free to do these two options. And some people use this one, some others choose this one. The advantage of this one is that I have an exact incompressibility constraint. In this one, it's weakly imposed, so I have some kind of, in an integral sense, is satisfied. Now, what we try to do is that, okay, can we solve the two equations at the same time, and can we link them together? And we did this linking by using the vorticity. So in a nonlinear term, we use the vorticity solution from this set of equations here, and here we use the vorticity from this equation here, and we link the two equations together. So, and this has some quite nice properties, and we also did it for MHD, and I will just finish with this example. So this is for MHD. So MHD is just Navier-Stokes together with Maxwell, and we solved again with these two sets of equations. And this is an example. This is Orszag-Tang vortex test, and this is the current, and it creates these very fine sheets. Of course, we cannot go very much further than this because then we don't have enough resolution and this breaks. But this is quite difficult to even to reach this point, and with this decoupled or coupled formulation, we managed to do this. Yeah, and that's it. So some conclusions. So the point is this: it's important to understand what is the underlying mathematical structure of PDEs, and one important thing is this: the Rham complex. So we cannot represent all unknowns in the same way. They need to be represented in different ways. Otherwise, it's very difficult to satisfy this divergence of the curl equals to 0 and curl of gradient equal to 0. And this has impact on the numerical results. So numerics should reproduce a discrete Rham complex. And then the invariants are also important. So when you have time-dependent problems, and then as was discussed, we need to find the correct formulations of the physically representative formulations for the PDEs as a starting point. If we don't do that, then we get also bad results. So I showed some applications to these problems. Now, in terms of open problems, there are many. So one of them is preconditioning, for example. How can we precondition this type of equations? Other things is how can we actually do hybridization? This is also for fast solving the problem. That's it. Thank you. for Navier-Stokes? For Maxwell's? Just for this presentation, just because it would be a bit, it's already too much. So do that would be too much, but indeed you can do that. You can do that, and you can even do, and also for the wave equations, for example, for acoustics, you can even do that. So Maxwell's, you can directly do it in four dimensions, so space and time, and you can get a space-time formulation, which is, if you take these in differential geometry, you can extend it to 4D, so you have a space-time discretization. And we started doing some work for the wave equation, and we get a discretization. Just we take these principles, apply it into a, in this case, 3D, so 2D space and 1D time. That is conservative and this kind of thing. For Navier-Stokes, there are more problems, and that's one active area of research, because it's much more complex, the structure there. Because, for example, velocity. So in Maxwell, we have two types of magnetic fields and two types of velocity fields. But this is very simple to relate the two of them. For Maxwell, we have the velocity, which in the, for example, in this form, let me put it here. In the rotational form, there is this velocity that appears here, which is a vector field. But then there is this velocity here, which is not velocity, is the momentum. And it has a completely different structure than U. So this is one of the challenges that we are having now. Yeah.
Yeah. How would you choose which structure you preserve? I mean, that may mean, what I mean by this is that you cannot preserve them all. Preserving some may mean breaking others, right? So maybe the point there is that you need first to understand which structures are physically important to actually being able to design the scheme you want to. So I'm not so sure that basically delving into the mathematical structure is what's going to help you most. I think insisting on the physical structure, I mean, essentially where it comes from. And we don't know everything. For example, for Navier-Stokes, it's simple, right? There is an infinity of quantities that you may want to preserve. Or maybe they are important. People studying turbulence say, maybe we will find the particular invariant which is fundamental to turbulence, right? They haven't found it yet. But the point there is that you need first to look at the physical structure. And before, maybe you look at the mathematical structure.
I agree with you, but I also don't agree with you, in the sense that I agree that the physical structure is fundamental. But the point is that this mathematical structure, the Rham complex structure, if you don't satisfy it, you don't satisfy the physical structure. Because the physical structure stems or derives from this structure. For example, if you go to Navier-Stokes and you get energy conservation, it's, for example, fundamental that the gradient is a transpose of the divergence. If that's not the case, then you don't have conservation of energy for it. For example, yeah. But I would say, I'm not going to claim that for all cases this is essential, but at least for all the cases that I studied, so MHD, Navier-Stokes, and electromagnetics, shallow waters. So in one part or another one, when you are deriving either conservation of enstrophy, helicity, or energy, these types of properties with the differential operators appears always there. So if you don't satisfy that, you kind of break it. So the part I disagree with you is that I think that at least this structure is essential to get it right. And then I completely agree with you. The physical structure is essential. Yeah. 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 It doesn't solve all the problems. No, I agree. So and my history was exactly that. So first focusing on the Rham, and then time-dependent problems, it breaks, and then I need to look to something else. And the key point is to identify what are the fundamental physical properties that we need to conserve, depending on the problem. And even for the same problem, maybe we are looking more at something than something else, so we need to, it's a trade-off.
There any other question? I have one. So the location, when there are multiple variables, we cannot I mean, the choice of where we locate the variables is important to then analyze the properties at the discrete level, right?
Yeah.
So if we make a particular choice, then we might not have a discretized. So what I'm asking is that there is this paper where it says that if you use cell-center variables, you cannot conserve mass, momentum, and energy at the same time. And this is just imposed because you are using cell-center variables. So if you want to conserve the three properties, then you are obliged to use another kind of.
Yeah. I mean, there are, for example, Blair-Perot, he claimed there is this box, the Keller box scheme, which I found it very surprising, but at least for first analysis, it doesn't fit necessarily in the, it's slightly different way in which it fits to this, but it's not exactly like this. And it's a very nice scheme and conserves a lot of properties. So I imagine that there are many ways, many different ways of doing it without exactly satisfying this exact form. But I think in the end, the point is this. Once you define your unknowns and how you represent your unknowns, underlying there is an interpolation. In some discretization, this is not made explicit. In finite elements, the interpolation is explicit. And when you do this, then the differential operators automatically are defined, or the correct ones are defined. That's my claim. And then how you connect these two things, so how you connect the two grids if you have two grids, or how you do the approximate version of these operators, the weak ones, then it's a bit of an art of how to do that.
Thank you very much. So Artur is here until Friday if somebody is interested in discussing with you. Thank you.
Thanks.